Hello again, student. As I told you last time, today we are going to introduce the practice number 3, where the students have to be able to make a supergear of that specification. When I say a supergear, means that the tip of gear is parallel to the axis of that gear. Not only supergear, but also helical gear, bevel gears, rake gears, and pinion, but at another level. At your level, I want you to master how to produce a supergear with parallel tip. So now, as we discussed together last time, we have seen that the general mechanism of dividing head every time is very helpful for producing these parts because there is a division of teeth. So we start by calculation. There is some calculation which is related to the gear manufacturing process. First one, when you check on your drawing, you see the gear you have is 4-moded, 6 teeth, and the 20 pressure angle, 20-degree pressure angle. This pressure angle is coming from to the structure of cutter. When I see the specification of gear cutters, you see here there is a 20 PA, means that 20-degree pressure angle. Means that this type of cutter, if it is used to produce this kind of cutter, it will take this kind of specification. That's why. Means that while you are selecting the milling cutter, you have to base on flowing specification, 20 pressure angle, and the 4-moded. You have to look also the model number. It's like the size is how to classify the size of milling cutter for gear production. This is the model number 2. 2 model number 2. There is a 2 model number 1 and the 2 model number 3. Means that is the 3 number of milling cutter for producing that gear. First one, use number 1. Second one, use number 2. For finishing, use number 3. So last time, I told you that there is a milling operation classification. I want you to tell me which kind of classification are we going to be done in this operation. You remember well, I explained well what we call forming operation in milling classification category. Is where we are going to perform this task. It means that the form of teeth comes from the geometry of the milling cutter. That's why we say forming operation as the category of milling operation. So here we have to calculate, first of all, calculate outside diameter, which is specified by OD is equal n plus 2 times model. N is the number of teeth. M is model. OD is outside diameter. The calculation of outside diameter is very important because you cannot achieve on this task without preparing the blank of GEA. When I say the blank of GEA, is a turned a workpiece which will be used to be manufactured from this for producing the GEA. The outside diameter I'm saying is that measured diameter. It means have to be calculated from this formula. It's better to respect that. If you don't respect, there is no standard GEA you can make. If you respect it, as long as you have the specified milling cutter, you will achieve the standard of GEA. If not, you cannot achieve. That's why this formula of calculation outside diameter is very critical, since there is a parameter of number of teeth and also a model specifying the size of the milling cutter. So after that, you have to calculate the indexing method. So here, the direct indexing can be applied 24/16. Is it divisible? Not. Means that the direct indexing method cannot be applied to produce this kind of super GEA. Let's see the plain indexing method. Say that 40/n, n is the number of division, means that 40/60. It will be, we get 40/230. Here we get 680/16. We can check the availability of indexing plate. I explained it before. This is indicating the whole cycle. This is indicating the whole have to be added after 2 turns of indexing crank. Here we have 16. Can you look here? Where? You see here where? The first whole cycle is 16 holes. Means that we have to select that whole cycle, where we have 16 cycle hole to add 80 holes after full index crank. So now we add just indexing pin. You see now the indexing crank pin is engaging in a 16 hole cycle. I have to perform this work by using this setting of indexing plate. Let's check if indexing it is rotating. Good. So this diameter, this blank GEA have been done on a left machine. I think you have performed well. Your task have been done good. Let's check outside diameter. This is 7.2. It's okay. Now let's check the module. Here there is module 4. It means you have to use this cutter. Module 4. Do you see? It's the module 4. This cutter will be used to produce this kind of GEA. Now we have to mount this cutter. Okay, good. The vertical arbor is mounted with the milling cutter. We have to fix the workpiece properly in the So before setting the cutting tool to the blank gear, make sure the milling cutter is in the center of the workpiece. I have to check that. I think you know how to use the vernier H gauge. 160 millimeter. We have to, here minus the half of this workpiece is where the center is. Means that 160 128 is the center of the milling cutter. I have to set the vernier H gauge in 128. So now, clearance positioning. So the indexing, after calculating the indexing method, you have to calculate the depth of cut. Depth of cut, consider this constant times the module. The module is 4, means that we get 8.5 millimeter. The depth of cut is very important because it's where you can meet the standard of gear. Now we can choose the direction of cutting. Because of this milling cutter has the clockwise direction, you have to choose this direction. But you have to reduce the speed. Okay. Good. So now we have 2 full turns of index crank plus 80 hole on 16 hole cycle. You are going to see the importance of indexing plate. We have to account where the 80 holes, which will be added after 2 full turns of index crank. 1, 2, 3, 4, 5, 6, 7, and 8. Means that after 2 turns of index crank, I have to add 80 holes on 16 hole cycle. Clearance positioning for setting the cutting depths. That's the coolant to spread out. So the first formal surface of GRT already produced. Now indexing. 2 turns of index crank plus 80 holes on 16 hole cycle. 1, 2, and add 80 holes. Then move the sector arm. Cut again. You see already the first tooth already produced. Now the second one. We start indexing again. 2 turns of index crank. 1, 2, and add 8 cycle hole. Good. Feeding again. Back to the original position. Then indexing again. 1, 2, plus 80 holes. Now the process is ended. So this is a super gear. It has been produced, of course, while you are seeing me while I'm producing. We have 16 teeth, the 4 module, and also the depth of cut is 8.5, as we have calculated. Yes, 8.5, as it has been calculated. 2.127 multiplied by 4 is equal to 8.5, is the depth of teeth. So at the end of process, remember to clean the machine. It's very critical. Move away the sheep have been produced, then clean the machine and put the oil for the maintenance purpose. Then shut off the machine by emergency, and also shut off the main switch, safety switch. So dear my students, we can conclude the lesson for the milling operation practice. So first of all, every student have to be able to classify the milling machine category based on their access. The students have to be able to identify the many parts of milling machine, as we have seen together. And also the students have to be able to calculate all necessary calculation needed for indexing process, such as direct indexing and the simple indexing or plain indexing method. And also the students have to master the indexing plate. Indexing plate is very important because if there is no indexing plate, we cannot account apart from those fractions. 80/16, how you can account this fraction? The indexing plate is there to resolve this challenge. You can count 80 whole on this whole cycle. It's there for resolving this challenge. How you can account the 6 full turns of index crank plus 80 holes, means that there is no full turns here. It's a fraction of turns. That's why the indexing plate is very important. You have to be familiar to use it, and also to be familiar with simplification of fraction to meet the availability of the indexing plate in the workshop. And also the students should be able to how to calculate the depth of cut based on the diameter of board. Here we have to remove 6 millimeter on this material, but on diameter, on radius, you have to remove 3 millimeter. Because the workpiece is rotating, means that 3 millimeter should be on diameter 6 millimeter. So now I can close by thanking you. Thank you for kind attention.